Alright, we're going to learn about RL circuits. So what RL circuits are, it has resistors and inductors. Inductors are basically a coil of wire in a circuit that creates a magnetic field. And it stores that magnetic field until there's a change in current, and then the magnetic field will produce a current to keep the current relatively constant. So basically, inductors do with current what the same thing that capacitors do with voltage. So everything that goes into an inductance equation are these things. An inductance is denoted by the letter L, and it also looks like this within a circuit. So all of these components go into what inductance is. So the magnetic permeability of the metal and the Nagaoka coefficient both pertain to the specific metal that the current is running through. And then these three, number of turns, cross-sectional area, and length of the coil, all pertain to the actual coil itself. And inductors use current to generate a magnetic field, which means the current is going to increase slower. So this is the max current right here, this dotted line. So as time goes on, it's going to gradually reach that max instead of going straight up and reaching it, because some of that current is being taken away to make a magnetic field. And then, as I said before, if the current drops, the magnetic field created by this inductor will create more current in order to compensate. So if we go to a problem here, we have a 12-volt battery that's in series with a 10 ohm resistor, an open switch, and a 200 millihenry conductor. Henry is the unit for inductors. So I've drawn that out here. And then we want to know, what is the current flowing in the circuit after the switch has been closed for a long time? And the significance of the switch being closed for a long time is we don't have to worry about this curve right here, because we're saying we're right here where the current has already reached its max value. We don't have to worry about the inductor taking any current away. So this one is pretty simple. We already know how to do that. So it's I equals V over R. Current equals voltage divided by resistance. And we know that the resistance of this circuit is 10 ohms because we have a resistor right there. We know that the battery is 12 volts, which means we just do 12 over 10, 12 volts over 10 ohms, which is equal to 1.2 amps. So that one's pretty straightforward. So I'm going to go to the next part of this. So we want to know what's the value of the time constant tau. So we have our equation, tau is equal to L over R. L, once again, is the inductance, so it's 200 times 10 to the negative 3 henries divided by, again, 10 ohms, and that is going to be equal to 0.02, which is going to be our time constant for that inductor. So then we want to know how much current will be flowing in the circuit after 10 milliseconds. So this is where we need to worry about that curve of how the current increases. So we have t equals 0.01 seconds, which is 10 milliseconds. And then our equation is going to be I equals I naught times 1 minus e to the negative t over tau. So if we do I is equal to I naught is the 1.2 amps we got in that first part. That's the initial current. Times 1 minus e to the negative 0.01 divided by 0.02. That's our time and then our tau. That is going to be equal to 0.472 amps. So see, at 10 milliseconds, we're still taking current away from the circuit in order to form that magnetic field, so this is going to be less than the 1.2 amps that we're going to reach eventually. So part D, what is the voltage across the resistor and inductor after 10 milliseconds? So we know that V equals IR. So if we do V equals 0.472, because that is the current at 10 milliseconds when we want it, times R, which is 10 ohms from that resistor, the voltage over the resistor is going to be 4.72 volts, and that's going to be a voltage drop, so I'll mark it negative. And then we know from our rules that the current has to be, or the voltage, voltage has to be down to 0 by the time it gets back to that battery. So if we lose 4.72 volts over the resistor, that means the rest of that current has to be lost over the inductor. So if we do 12 minus 4.72, we're going to get 7.28 volts dropped over the inductor. I'll again make this negative because it's a voltage drop. Alright, part E. At what rate is the current changing at this instant? So that we're going to use this equation. So epsilon is equal to negative L delta I over delta T. So epsilon is our EMF, which means it's the voltage we just calculated in that one. So negative 7.28 volts, because that's the voltage drop over the inductor, is equal to 200 times 10 to the negative 3 henries delta I over delta T. So that is going to be equal to 36.4, because amps per second, because this is our amps and this is our seconds, so we don't need to worry about that. So we just solve, this is times L. We just solve for L right there. And then for part F, how many time constants will it take for the current to reach 99.4% of its max? So that's, again, we're going to be looking at this time versus current graph, where the current max is up here and it's going to take its time getting up there. We want to know when it's at 99% of that max current. So our initial equation we used before was I equals I naught times 1 minus e to the negative t over tau. So if we divide by I naught, we're going to manipulate this equation a little bit to make it easier to solve. So it's I over I naught is equal to 1 minus e to the negative t over tau. This side we can add e to the negative t over tau and subtract I over I naught, which will then get us 1 minus I over I naught is equal to e to the negative t over tau. And then we can take the natural log of that whole thing, which will let us end up with negative t over tau is equal to ln 1 minus I over I naught. And then we can multiply by tau to get it to the other side. Actually, we'll multiply by negative tau to get rid of that negative. So we'll get t equals negative tau ln 1 minus I over I naught. So from here, we solve for time, which is what we want. So for I over I naught, we can plug in 99.4 from the problem up there over 100. And then we want the natural 1 minus that, and we take the natural log. So it's going to be t equals negative tau times 5.116, which means it's going to take 5.116 time constants for it to reach the max current.